It's a great opportunity and privilege to share a really exciting but challenging project that we've been working on. The project is about designing and further testing a self-configurable supply chain model that we've been working on for the last 2 or 3 years. We presented a first version last year at the same conference, one that we've developed for BHP Billiton for potash supply chain mining operation. So the presentation outline, I will start off with just a short introduction of Gold Research Labs, and then specifically highlighting what the research objective was of this specific project. As I mentioned, further development and testing of the self-configurable supply chain simulation model. We used it in this case to assist Microsoft with designing a world-class supply chain using theory of constraints principles, and then testing whether that solution design will actually deliver better results. And by better results, we mean both operationally better results, less shortages, less surpluses, shorter supply lead times, better ability to respond and be responsive to changes in demand. And secondly, to then implement the rules, those theory of constraints rules, directly within their standard SAP system. Part of the project included a pilot to test whether the rules are working exactly as we predicted and delivering the results that we predicted from the supply chain model. I'll provide a short overview of how the model works and share with you a short demo of how the model works. The results that we've achieved, the lessons learned, it was an extremely challenging but very exciting project. We started with the project in September last year. By mid-December, we already went live with the first rule set from theory of constraints directly into their SAP system, and has been rolling out additional rules in their SAP system on a monthly basis, and have one to go, and then the whole project would be finished in less than 9 months' time. So let me start with just a short introduction of Gold Research Labs. We're very passionate about helping organizations answer 2 simple but important questions. How much better can you do? A little, considering all the past improvements. Could it be that there's not much to squeeze out from your existing operations or supply chains? Or can you do a lot better? Is it possible to get another step change improvement? And then second question, what's the best way of doing it? What's the simplest, fastest way, the lowest cost, the lowest risk? We're privileged to work with some incredible organizations around the globe, both from the private sector as well as from the public sector, and with incredible partners like Amalgama, like AnyLogic, and SAP. So what is our research project objective? At our Gold Research Labs, we use a very robust research method. We look for performance or expectation gaps, and then help our clients challenge the basic assumptions around those performance or expectation gaps. When there's a large performance or expectation gaps, the common way of dealing with it is to challenge the assumption that our expectations are simply too high. We should lower our expectation. That's one way of closing the gap. But of course, there's another way of closing the gap, which is being willing to challenge the assumptions on which your actions or decisions are based to realize those full expectations. And in this project, and one of the simulations that I'll show you at the end of my presentation, I'll show you that it's possible in many cases to dramatically close those expectation or performance gaps if you are willing to change the rules, if you are willing to look at better, more global optima rather than local optima rules. So the research project objective that I'm presenting today, as I mentioned, is designing and testing a self-configurable supply chain model to identify improvement gaps, help our clients identify how much better can you do by comparing their past actual performance, re-simulating that time period to show what would have been possible if they had been using different rules. A very ambitious target, and we remained skeptical for a long time whether it's actually possible to do something like that. So let me show you how the basic architecture works. As in this case, Microsoft uses SAP as their global ERP system. We run a query that is extracting data directly out of that SAP system in a template that we've provided. That template includes all the data that we need to fully model their global supply chain, end-to-end supply chain, all the way from tier 2 suppliers, tier 1 suppliers, contract manufacturers, distribution centers, tier 1 customers, which includes their online store, their physical walk-in store, as well as tier 2 customers like a Best Buy retail outlet. So we have defined a template that includes all the data that we need to self-configure that whole supply chain model. On top of that, we also read in data that is showing us what the actual customer orders on the distribution centers were over the time period that we want to simulate. We also read in what the actual forecasts were at the time, so we can test how sensitive rules are to forecast error if that's part of our rule set. And lastly, we are also reading in the actual stock on hand for every SKU location, every stock keeping unit location in every part of the supply chain. So we can compare if we are running that simulation time period with the new rules, theory of constraints-based rules, could we have done a better job? Can we actually see less shortages and surpluses? So that's how the process starts, as a query that is run. It exports data directly into Excel. As I mentioned, it contains all the information that we need to model this supply chain. On top of that, we read in additional data that we receive from the experts, which includes the randomness around, for example, supply lead times. You might have in the item master supply lead time of 30 days, and that would be what is read in from the ERP system. But of course, 30 days isn't 30 days, so we can also read in what the randomness around that was. What's the fastest that they've ever delivered? What's the longest that they've ever delivered? And what is the mean like? And that allows us to bring in randomness. On top of that, we can also bring in random events, both planned and unplanned maintenance or downtime events, so we can run 1,000 iterations and see whether we ever have a perfect storm where all of these random events combine. We bring that into a custom-developed AnyLogic model that has a very simple user interface to manage the scenarios, make selections about which rules you want to run the model with, what time period you want to run the model with, which products, which channels do you want to run the model with. And our model has got embedded in it theory of constraints best practices of how do you manage make to order or build to order, assemble to order, make to stock or make to availability. It models a number of processes inside of that, and then the output of that is then displayed as reports visible directly from the AnyLogic model. We also export the data into Excel reports as well as into logs that help you to identify and do diagnostics if the results that you're getting doesn't meet your expectation. The model that we've created can be run in 3 different ways: a single experiment run, which I'll show you a demo of, a sensitivity analysis to test how sensitive certain parameters are to the outcomes, and of course you often get surprises where something that you thought would be quite sensitive turned out to be completely insensitive to the outcome, and others that you thought were very insensitive turned out to make a big impact. So each of the rules that we've implemented within the model, each of those parameters in the rule, if you click on them, you can do a sensitivity analysis on it. So what is the theory of constraints best practice solution for managing supply chains? Just a show of hands, how many of you know about theory of constraints? Very good. So just a brief explanation. People often ask me, why is it called theory of constraints? Well, in science, theory is simply a good explanation about something, why something is important. And a constraint is extremely important. Knowledge of a constraint is extremely important within management of complex systems that are governed by uncertainty and interdependency. In 5 ways. If you know the constraint of the system, it determines the theoretical maximum that that system can produce. So knowing the constraint and its capability helps you to set ambitious but realistic targets or goals for the system. Secondly, the real constraint in any social system, as you probably know, is management attention. Why? Because the demand on our limited attention will always exceed the available attention. So knowing where the constraint is helps us decide where to focus that scarce and very precious resource of management attention. The third element is it helps us to provide us with a quick shortcut of judging the impact of any changes on the system. If I know the impact on the constraint of a change, I know the impact on the whole system. Does it make the weakest link stronger? Yes, it will help the system. If it doesn't, it won't help the system. And the last two parts why it's really important is that it turns out that the rules that are needed to optimize the constraint, make sure the constraint is never starved or blocked or overproducing or wasting capacity in other ways, is also the global optimal rules to optimize the whole system. And that's normally very counterintuitive from a local perspective. So knowing where the constraint is and what is needed to ensure that that constraint is never starved or blocked or overproducing gives us, again, a shortcut into what are the rules that are probably needed to optimize the whole system. And the last part why it's really important is it tells us when we have to change the rules. If a constraint moves, you have to change the rules. So guess what? Every time a constraint moves and there's a lag, you get suboptimum performance. So part of our design is to keep the constraint in one place. So let me show you how we go about. There's a big difference between the generic principles behind theory of constraints and practices like Toyota Production System, Agile and others. They are all based on exactly the same governing principles that are very generic, but the applications are very specific. So when we design a system, we look at what's our objective, effectively and efficiently meet the demand, how to do that to continuously improve and synchronize the flow of work throughout the system. And we can categorize the decisions that we as managers make into three categories: planning, which are decisions that we make before we start work; execution, which is decisions we make while we do the work; and measurement and improvement, which is decisions we make after we've completed the work. And in each of these, there are key decisions that we have to make. The purpose of this presentation is not to take you through all of them, but just to highlight, for example, one of those, and you will have access to the slides and most welcome to send me any questions if you might have. So we look at what's the decision we make, what's the common mistake that we make in making that decision, and what is a better way, a more global optimal way. I'll just focus on the first one, is how do you actually allocate resources and buffers in your system? Well, the mistake that we make is we allocate resources way ahead of time based on forecast, and all that we know about the forecast, it will be wrong, so you'll end up with too much resource in one place and too little in another place. So what's a better way? Well, allocate only what you absolutely have to, keep the resource central, aggregate it, and allocate it dynamically once you know how much you need. A typical example of this is the terrible experience that we see in especially governments with spend it or lose it, where you are allocating budgets ahead of time, and because you've either allocated too much or too little, where there's too little allocated, they need more money. If there's too much allocated, the manager is in this horrible position where they have to spend it or lose it. And the consequence of that is at a federal level in US is that on average you're spending about 30 to 40 billion US dollars on external contractors a week. In week 52 it's $150 billion. So really terrible consequences when you get these wrong. So how do we translate these into a specific design for a company like Microsoft? So no need to introduce Microsoft. It's one of the largest companies in the world, over $90 billion of sales. More and more, their sales are coming from selling physical devices. It has a major upside, but also a downside, that it exposes you to increased levels of complexity and uncertainty. They've got over 5,000 SKUs, very large variation in product life cycles, 10 contract manufacturers, over 12 DCs, more than 1,000 tier 1 customers, and even more tier 2 customers. And our objective was, can we come up with one DSC, one digital supply chain? And it played on two elements: one way of managing the supply chain, one set of rules regardless of the devices or the order fulfillment strategies that you use, and secondly, those rules implemented within one system, which is standard SAP. So we use a software that we've developed ourselves called Harmony, that you can have a look at harmonytoc.com, to build these strategy and tactic trees that shows us exactly what are the rules that we have to implement to achieve, in this case, a world-class supply chain performance, which is a necessary condition to turn supply chain performance into a competitive advantage, which again is a necessary condition to achieve profitable growth. And there were 6 rules that we had to change. The first one is, how do you decide on an order fulfillment strategy? Should it be make to order, assemble to order, make to availability, or building to a number? How do I buffer those, creating time buffers for the assemble to order, build to order? How do I ensure that I have sufficient stock of parts and goods? How do I control the release of work in process between all of these? How do I maintain a single priority system within all those order fulfillment strategies so that when somebody gets a listing, regardless of the order fulfillment strategy, black means you out of stock or over time, focus on that, then red, then yellow, then green. And lastly, how to systematically improve flow. Each of these rules are broken up into a lot of detail, trying to understand the specific objective of each of those, or the strategy of each of those, the tactic, and then all the assumptions, and then defined in a great level of detail to provide a picture for people, in this case, for example, the internal resources and SAP consultants, to explain to them exactly how the rule works, and showing how that rule will be implemented within SAP. We are using the simulation models to test whether the logical explanation that we thought that by implementing this rule we'll get better results will actually be worth it. So just to quickly show you, so the simulation model, it starts off with creating a very simple user interface. You load up the file that has been exported out of SAP that contains the data. You immediately get a view of what data has actually been imported into the model, the time period, the supply chain configuration, the types of products and categories, the demand profiles. You can also do a selection about whether I want to run the model backward in time, comparing whether the new rules would have given better results, or I can run it forwards in time. The only thing I have is a forecast, for example, and I can create random customer orders with a forecast error to see how robust or fragile my supply chain is in terms of coping with demand that maybe is 20% higher or 20% lower than the demand. And I can select the rules to use and finally the scenarios I want to run. So I can also look at the map. This shows me the data that I've imported, the self-configured supply chain, what it looks like. And I can also look at cumulative flow diagrams. In this case, I can see the demand forecast, which is the red line, is actually below the actual customer orders that was read in for this specific product category, which already tells me if they were producing to forecast, probably they will have some shortages, and the shortages will not be a result of capacity, which is the orange line going above. There's more than ample capacity, but simply because they are producing to forecast, they will have shortages if the customer orders actually exceed. So I think this is where if you can just activate the video here. So as the video is playing, so you simply click on the data file that you want to import. It now imports the file. As it's importing, it's self-configuring the whole supply chain. You can immediately see what data you've imported, can make selections about which products to run, what time periods to run. Whether you want to run forward using forecast to generate actual demand with a forecast error, or to use actual demand and forecasts, and select which rules you want to run it. See what the actual map looks like, the supply chain configuration, going into those cumulative flow diagrams to just have a look at what the data is telling you. Is the actual orders that I've been read in, is it more or less than the forecasts? And then you can start running the model. It takes a few seconds to load up, and then you have a dynamic simulation model. In the background, what's happening is we are simulating around 30,000 to 50,000 events per second. Every single event that's happening in the supply chain, you can click to see the financial performance. You can zoom into specific parts like the contract manufacturer to see the orders that are being placed on that contract manufacturer automatically prioritized by the colors. You can see if the backlogs are building up or whether it's stable, so we can quote lead times. You can look into the stocks at the contract manufacturer to see if our new rules are managing those well. And we can zoom into a specific DC and go into a specific product within that DC to see the purple line was what the actual stock was and the blue line was what it would have been with our theory of constraints rule. So the pie chart there is showing us what the causes are of the reds and the blacks that help us to identify where to focus our continuous improvement. And in this case, you can see the actual stocks were around 100 million. With the TOC rules, it would have been about 20 million, and we would have had less stock outs, unsatisfied demand. Can we do even better? You can simply rerun the model with a different rule that we've created, in this case a hybrid rule that is looking at end-of-life items and peaks in demand. We can rerun the model. It takes about 7-8 seconds to run a full year. And you pay attention to the blue line, which is the actual the performance with the theory of constraints rules. You can see stock holding now is less than 20 million, and we've reduced our unsatisfied demand even more. And can again zoom into specific products, see the actual stock on hand and what it would have been with our theory of constraints rules. So it provides a lot of usability for the users. We've realized very quickly on is that why is there such an inconsistency between the value that simulations can bring and the number of people that are actually using it? And our hypothesis is very simple. It's still too complex to use. It takes too long to develop these models. And this is the problem that we're trying to solve here with this type of self-configurable model. Here is a simulation that was run by one of the planners. They've gone in, they've simply changed a production line that was utilized only 50% of the time to have only one production run rather than two, and it quickly showed that by reducing that capacity, they will have massive backlogs building up, so it's not a good idea to do that. And just to prove to you that you literally, it self-generates, so we've opened up another file, a much more complicated data set file, and again, you can pull it up, you can see it's completely different supply chain now of data that you've read in, much more complicated in this case. When you zoom in, you can actually see the transportation units, the trucks, the ships, the planes moving around. If you want to, you can zoom in even further, and if you've activated that button, you can actually see the trucks following the roads, which is a greater functionality that AnyLogic has given us with this geolocation. And again, I can zoom into specific products, in this case, many more in this distribution center, and testing a specific order fulfillment strategy, which we call BTX, or build to a number X. And you can see how our rule is automatically building up stock levels based on the limited capacity of the contract manufacturer, and comparing that with what actually happened, which is the purple line. So the purple line is always the actual stock on hand that they had, and we're now comparing it with what it could have been had they been running our theory of constraints rule in fully automated mode. So it proved the hypothesis that these theory of constraints rules can provide at least the same and in many cases much better results than previous rules that have been used, and it can be implemented in SAP literally in a touch-free environment, releasing the planners to focus on those things that are really important to them, doing expediting, diagnosing why things are going wrong. So some of the lessons that we've learned, is it possible to do this? Yes, it is, but it's not easy. We are in an ongoing process to work on how to create a template in a way that it makes it much easier to populate it with exactly the right data. We've got a number of other projects happening at the moment with, for example, Cargill on their supply chain, supplying chicken into McDonald's and other retailers, and also with Tata Steel, so testing it across different industries. And what we're seeing is that dramatically reduces the development time here from months to literally weeks. It makes it much more accessible to users because they don't have to develop these models. They simply get the data that they want to look at, click on the upload button, and it loads up the data, and the model is there, and I can click on run, and it runs. We've done extensive field testing. We've seen that it's an extremely useful tool to support decision making, especially in environments where there's lots of complexity and uncertainty. And it's also a great training tool because people can actually see how the rules work. They can slow down the model. They can run it again and again to build up some intuition about these often counterintuitive global optima rules. And lastly is that, at least in Microsoft's case, the next phase in the project is integrating this model directly into their sales and operations planning process to help them make better, faster decisions, to do what-ifs. For example, you can now download the status of the supply chain as it is now, the stock on hands in every single node. We've had a strike report, a contract manufacturer has gone down. What's the best way to respond? We can run multiple what-if scenarios using the data as it is today to see what's the best way to respond. Our vision to help partners like AnyLogic close this gap between the value that simulations can bring and the few people that are actually using it at the moment is to develop mains apps. We've found a way of being able to convert the Java apps that we get directly out of the AnyLogic model into apps, native apps. So if you go into the Apple OS X store at the moment, you type in Goldratt, you'll see a number of these models that we've created that you can download, and we offer for an in-app purchase, we offer the ability to customize these models. So the basic model includes a default set, so you can see what the rules will do, how it works, the magnitude of the results that you bring. And I'll end up with just displaying this little video to show you how one of those simulations work, one that we've developed in partnership with Realization. Many of their clients are from the Department of Defense maintenance depots, and this simulation shows 4 rounds. The first round that you see running at the moment is showing what the performance will be for a maintenance depot that's got 100 planes that they have to maintain, what the performance level will be if there's no variability in demand or supply. And you can see we're achieving a fleet performance availability of around 72%, so about 72 of those planes are operationally ready. And what we can do is to see how much the performance deteriorates if we simply add variability in demand and supply. So in the demand side, maybe we get 24 F-19 fighters a year to maintain, but they don't arrive very nicely to a month. They sometimes arrive 4 or 5 and then nothing. And you can see by how much the performance have deteriorated. Availability is now 62%. That's another 10 planes missing. Costs have gone up by 20%. And now we can test in round 3, what if we use the theory of constraints rules just in the depot to control the work in process, make sure they don't start working on a plane without a full kit, don't multitask. And we've already achieved substantial improvements. We've got another 2 or 3 planes back in operations again, but we still have problems with the availability of parts. So the last round is what if we synchronize the whole supply chain and we are dynamically resizing stock buffers throughout the supply chain, not based on forecasted demand, but based on the actual demand that we're experiencing. And what you'll see is we get very close to perfect world maintenance again. Obviously, this project was extremely challenging, so just to end off with, I just want to thank all our partners. Again, Dr. Andrei Malikanov from Amalgama, thank you very much. Him and his team worked very, very long and late night hours with us. The team at SAP and AnyLogic, the support was excellent, and then specifically the team at Microsoft, Robert Meshu, who's the CTO of Global Supply Chains, Shane Collar, who was at the time the Global Planning, Senior Director for Global Planning, and then the team that worked very closely with us, Manohar Madeira and Andrew Boucher, who were the program directors. Just a big thank you for them. We all put in a long, long hours and are so proud to present this project to you today.
How do you deal with policy departures, say like an inventory policy in a warehouse? In the model, it might be one way. In reality, we know warehouses kind of do their own thing sometimes. So how customizable are those policies within your model?
Very good question. So we deal with it in 2 ways. The way that I showed you now is we are not trying to simulate how they actually work today, what we are doing is we're reading in the consequence of those policies in terms of what were the actual stock levels per SKU location over, say, a year period. And then we, using the new rules, simulate that same period, seeing could we have done any better. But we also have the ability to model scenario comparisons. If you were using a very old traditional min-max or reorder point, how does that compare? And of course, we can model to see, do they always comply? Do they have a policy that says, let's keep 8 weeks of stock, even though the replenishment times on some items are 1 week and on some items are 12 weeks? But the way that we've done this is we looked more at the consequences of the policies, and they were specifically interested to see that the results that we're getting, much better result in a purely touch-free environment. So these rules are being executed. And that met the objective of digitizing their value chain, releasing the capacity of people not to look at transactions that can and should be automated with systems like SAP, but to let them to pay attention to manage the exceptions. Thank you very much.